last time we did an example of Poisson's equation, or how to solve equations using finite differences. So now I'm going to make it a little more general. Still in one dimension though. So we have a PDE like this with variable coefficients. So we have a second derivative term that represents diffusion, and then a first derivative term that is advection, and then term with no derivative, reaction. So this is actually called a advection diffusion reaction equation. And then we have some right-hand side, which could be 0, but in case it's not, so that would be like some sort of source term. And we'll just work on the interval 0, 1, and then we use Dirichlet boundary conditions. So, using finite difference stencils I showed last time, we get these equations. So coefficient a of x is represented by its value ai, which is the same as a of xi. Now I'm using same uniform grid. So we divide the interval 0 to 1 into n plus 1 intervals. So that way, we're only going to solve for u at the n interior points, u1 up to un. So u0, so x0 is 0, xn plus 1 is equal to 1. So that means that u0 is just going to be alpha, left boundary value, and un plus 1 will be our right boundary value, beta. So I'm going to use ai, bi, ci to refer to the coefficients evaluated at those grid points. So we have ai and then uxx, so we just use the usual center difference for those. And then similar for the other terms. So bi, we use the center difference here also for first derivative. And then ci ui is equal to fi, which is defined the same way. That's just f of xi. Okay. So what this leads to, and this applies for I equals 1 to up to n. So now we have a system of n equations for the n unknowns, u1, u2, up to un. So we get a system of linear equations. AU is equal to F. So now I can write down what that system is. This is A, U, F. All right. So U is just a vector of our unknowns, U1, U2, UN. I need to make a little more room here. Now, F, you can see from here that our right-hand side vector has to include F1, F2, and Fn, just because of what's in the equations there. But I'm leaving space because for boundary terms, I'm going to need more than that. Now, as for what goes in the matrix, first of all, in row I, we only feature ui plus 1, and ui minus 1. So whatever's multiplying ui goes on a diagonal. Whatever's multiplying ui plus 1 would go on the super diagonal, and whatever is multiplying ui minus 1 goes on the subdiagonal. So the kind of matrix we're going to get out of this is what kind of matrix? If we only have a diagonal, subdiagonal, and superdiagonal?
Tridiagonal.
Tridiagonal. Yeah. So if we go through all of these terms and see what is multiplying ui, then we'll just put those entries along the diagonals, starting with I equals 1. So we have, so for instance, we look at this, what's multiplying u1, we're going to have a minus 2 a1 over h squared. Actually, what I'm going to do is, I'm going to factor 1 over h squared out of the whole thing. So from the second derivative, we're going to get minus 2 a1. And actually, what I'm going to do here is, as long as I leave enough space, I'm going to handle the second derivative part first. And then I'll go back and add what I need for the other parts. So this is our 1-1 entry. And then on the superdiagonal, corresponding to ui plus 1, I'm going to have ai, actually it's going to be just that, so I'm going to have a1 for I equals 1. And then no over contribution to the first row. The second row, so I equals 2, I'm going to have a 1 times a2, and then I'm going to have a minus 2a2, and then an a2. And this pattern is going to it's going to keep going. So you've probably seen in other classes this familiar pattern of like minus 2's done a diagonal and then 1's above and 1's below. Certainly that came up in 610 for a second derivative, but that's when you have a constant coefficient. Here we have a variable coefficient, so we have to use a different a value in each row. So like the next row would be, I should have more room for this matrix. A3 minus 2a3, a3, and so on. All the way down. In fact, I am going to make more room. In fact, I'm going to give myself as much room as I possibly can. I'm going to space these out a little bit more because I have other terms to put in here. So that'll keep going down to, for instance, the second to last row, I'm going to have an minus 1, minus 2, an minus 1, an minus 1, and then the last row I'll have an and then minus 2 an. So these are contributions from the second derivative stencil only. All right. So questions about where those values come from. Now, let's go back to I equals 1. So we have a1 times u2 minus 2u1 plus u0, but u0 is not among our unknowns, and u0 is equal to alpha. So that term needs to be moved to the other side. So that's going to impact this right-hand side element here. So I'm going to have minus a1 u0, which is alpha, over h squared. So that's the one of the boundary contributions. Okay, for the second term. And then similar down here, I have, for the last row, I have an times un minus 1 minus 2un plus un plus 1. But un plus 1 is equal to beta. That term also has to move to the other side. So you're going to have minus an beta over h squared. Okay. So now, if we only had the second derivative term, the diffusion term, we'd be done. Our system would be set up. But now we have to account for the B and C terms also. So any questions so far about the setup for second derivative? This one thing that's kind of a pain is how do you set up a boundary? How do you account for boundary conditions? You just remember to put these terms on the other side to account for, usually boundary conditions. And we saw last time for knowing boundary conditions, you have a little more work to do, like to solve for things, to see what to put in your boundary vector. Now for
question.
Yeah.
So, so over there with our boundary conditions and stuff, we have u sub 0 equals alpha, and so you have to like force your right-hand side vector with the f values to make that boundary value true. So why don't you in the u vector, why don't you also just be like, oh, that's u sub 0.
Well, actually, I did something I kind of did something like that last time, where at first I treated the boundary value as an unknown, so I had an extra trivial equation here, like u0 equals whatever value was, like a. But then I wanted to have fewer equations, so I to account for the fact that I know what that value is, to put it in here instead of listing among the unknowns.
Okay.
Yeah. We like to have as few unknowns as possible. Well, actually, the other good reason this came out yesterday was if eliminating unknowns leads to a more favorable structure for a matrix, like making it symmetric, that's a good thing, because that cuts your floating point operations in half. We like symmetry. Okay, it's similar for the B term, but we only have a superdiagonal and subdiagonal contribution. None of these diagonal entries are going to be touched by that. So for instance, for I equals 1, we're going to have B1 times U2 over 2H. So I'm going to have plus H over 2 B2. The reason I have H in the numerator is I already have a 1 over H squared in the denominator sitting out here. So I have to account for that. Where did my matrix go? Okay. And then we have another boundary term. So we have minus B1 alpha over 2H. Well, that has to move to the other side, causing a plus B1 alpha over 2H. And this pattern is going to keep going, like for instance, all the way down to superdiagonal. H over 2B. Oh, that's B1. So yeah, this is for U2, but B1. B2 plus H over 2B3, and so on, down to the end, plus H over 2Bn minus 1. And then, for the last row, we have another boundary term. So I'm going to have Bn un plus 1 over 2H. That has to be moved to the other side, but it's the opposite sign. So it'll be Bn beta over 2H. So notice in the second derivative are the same sign, because they have the same sign in the stencil. Here it's opposite signs, because they have opposite signs in the stencil. And I need to handle the subdiagonal also. So minus H over 2B2, minus H over 2B3, and so forth, down to minus H over 2Bn minus 1, minus H over 2Bn. Okay. Any questions about the advection term? Last one's the easiest to handle, the reaction term. just CIUI. So we only are touching the diagonal, and there are not going to be any boundary terms for that reason. So I'm going to add each diagonal entry plus h squared c1 plus h squared c2 h squared, not h. Okay, I'm really out of scoring apparently. H squared, not h2. There is no h2. What is wrong with me? Plus h squared cn. Okay, I'm going to put these entries in parentheses so it's easier to see where one entry ends and the other begins. So it turns out each entry of the matrix has two terms in it just for different reasons. Okay. And that's it. That's our system is set up. One thing that's unfortunate about this, though, is because of the advection term, if the B is non-zero, this matrix cannot be symmetric. So the system takes a little longer to solve. Generally, a symmetric system takes half the time to solve as an unsymmetric system with a similar structure. Just like with, as we saw in 610, Gaussian elimination takes 2/3 n-cubed operations, whereas Cholesky for symmetric positive definite matrix takes 1/3 n-cubed. Okay. So questions about how this was set up? All right. Now, I'm going to look at a somewhat different case in which we can get a symmetric matrix. You can actually tell up front because the PDE itself has a symmetric nature to it. So suppose we have this variable coefficient diffusion equation. So here we have one-dimensional heat equation, well, steady-state heat equation. So this is modeling steady-state diffusion rod, and this is coefficient thermal conductivity, and then f of x represents a source. Now, there's a couple different ways we can write this, because if k of x has a first derivative, we could go ahead and carry out the product rule and get an equation similar to the previous one. So we could write this as k x uxx plus kx ux is equal to f of x. And then we could just set up a system like we did before. The problem is, because there's a first derivative term, that would not be symmetric. So we'd rather not do that if we can avoid it. Another way of writing it is partial with respect to x, k of x, partial u with respect to x is equal to f of x. So what we have is differentiation multiplied by coefficient differentiation. So the PD itself has sort of a natural symmetry to it. And that's why it makes sense that we ought to be able to get a system of linear equations for this PDE, unlike the previous one, where the matrix would be symmetric. And we can, we just have to think a little differently. So what we do is, so to get a symmetric system, the idea is we're going to assume that this coefficient k of x, we're allowed to evaluate it at any point we want. So what we do is we approximate what's inside the outer differentiation operator, kx, k of x, ux, I mean by that is, if for our interval, we're using the same kind of uniform grid as before, and this interval between two neighboring grid points, refer to it as a cell. So the cell boundaries, we have our grid points, x1, x2, and so on. But this point, x3 halves, that's what I mean by a cell center, the midpoint of each subinterval. So using like a staggered grid, where we're taking advantage of the midpoints of each of these subintervals, can be helpful. So what I'm going to do is, if I approximate this expression at the center of each cell, so k of x I plus a half times du dx at x I plus a half. So the way that's approximated is, so I have my coefficient value, and then to approximate the derivative, what do I use normally? Neighboring points, I guess, for a center difference. So to approximate the derivative here, I can use the values of u here and here, which I already have, or I mean, that's what I'm trying to solve for, my unknowns. So that would be ui plus 1 minus ui all over h. So this is, because you can look at this two different ways. You can think of it as a forward difference from a derivative here, a backward difference for a derivative here, or a center difference for a derivative here. That's second order accurate, and that's the way, that's the viewpoint we're using. A center difference with spacing h over 2. Because what do you normally do in a center difference? You always have a 2h in the denominator. Well, we have that here, 2 times the spacing we're using for this, h over 2, because we're using, you think of it as a 3-point stencil, using these 3 points with spacing h over 2. Okay. So, now, what happens when if I'm approximating what's inside the parentheses this way, then I take its derivative with respect to x, and again use a center difference. So k ux x, so this expression, now approximated at an actual grid point, xi, looks like this. So I have the expression inside evaluated at, the whole expression inside evaluated at xi plus a half minus same expression evaluated at xi minus a half, so points on either side of xi, over twice the spacing between all of those points, but that spacing is h over 2, so down below I'm just going to have an h. So this again, this is also a center difference with spacing h over 2. So this is, and this is 2. But now, each one of these I can replace with this approximation right here. So that's going to give me, so for the first one, I already have that written down. So that'll be ki plus a half, ui plus 1, minus ui over h, And then for the other one, it's similar, right? Just shift the indices down a bit. Minus ki minus a half, ui minus ui minus 1 over h. And all of this is over h. So now I can, what I want to do is I want to group terms together according to what's multiplying each u value, because those are going to be my matrix entries. So when I group everything that way, I see Haley have a bunch of emails from you, so I'm hoping that's the code.
Yeah. What did I say? Good.
Okay. So KUX X at XI. So just cleaning up that expression here. I'm going to have KI plus a half UI plus 1 minus, and I'm going to have h squared. Every term has an h squared in the denominator, so I'll just put that there. Now, for what's multiplying ui, I have ki plus a half and ki minus a half, because ui appears in both of those first derivative stencils. And then I have plus ki minus a half ui minus 1, because we have a minus and a minus making a plus. So this kind of looks like a center difference second derivative stencil. If all the k's were equal to 1, then it's exactly what we would have. Yes, I am. Now it looks like that. So now I can write down what the wrong page. What the matrix looks like. So we get system AU is equal to F. I haven't stated boundary conditions, so we're not going to bother with those, but I just want to show you what the matrix looks like. So these are our diagonal entries, starting with I equals 1, 2, down to n. So I have minus k 1 half plus k 3 halves, and then minus k 3 halves plus k 5 halves, and so on. And then second to last row, so k n minus 3 halves plus k n minus 1 half, and finally k n minus a half plus k n plus a half. So those are my diagonal entries for what's multiplying ui, and then what's multiplying ui plus 1 goes to the super diagonal. So that would be whatever values on the right in these diagonal entries, that just goes into the super diagonal with a plus k 3 halves, k 5 halves, k n minus a half. And then whatever term is on the left here goes into the subdiagonal with a plus. So k 3 halves, k n minus 3 halves, k n minus 1 half. Okay. And that's the matrix. And what nice property does this matrix have?
Tridiagonal?
Besides that, yes, both. But this symmetric was the one I was mainly thinking of. That these entries match. So you can solve this using, for instance, this one, like for geometry boundary conditions, this matrix would be negative definite. So you can use like Cholesky with minus A and solve the system that way. Or you can use minus A with conjugate gradient, for instance. Okay, so minus A is, so A is symmetric, and minus A is positive definite. So that opens the door to Cholesky, if you want to use a direct method, or conjugate gradient, if you'd rather use the iterative method. Okay. Now, we're doing pretty well on time. We'll talk about 2D for a bit. A straightforward generalization of this equation to 2D would be where I have coefficient k of xy, ux, x, and then a similar term with derivatives with respect to y equals f of xy. So what I could do is use this kind of matrix on one-dimensional slices, like x equals constant or y equals constant, and using these same kind of stencils, where if we use index I for x and the index j for y, we'd have like I plus a half and I minus a half, or for derivatives with respect to x, or j plus a half and j minus a half of a fixed I index for derivatives, partial derivatives with respect to y. And I'll show later how we set these things up in terms of like the actual matrix when it's 2D, because you use things like Kronecker products and so forth. But the point is, similar ideas apply, similar stencils apply, and you can get symmetry in this case also. But what would happen is matrix A would be n squared by m squared, where if you're using the same number of grid points in both the x and y directions. Okay. Well, I'll briefly tell you now. Okay, so if A1 is matrix, well, actually, no, I'm about to make a wrong statement. When it's a variable coefficient problem, it's actually a little harder to construct a matrix. So I won't get into that right now. But I do want to talk about another 2D thing. 2D Laplace's equation, or Poisson's equation. So you just have Laplacian of u is equal to some function f. Then what you get is you have uxx plus uyy is equal to f. So that gives you so for derivative with respect to x, the second derivative with respect to x, ui plus 1j minus 2uij plus ui minus 1j over h squared. I'm using equal spacing for both x and y at h. And then second derivative with respect to y, the I index remains the same. The j index changes. Is equal to fij. So xi, yj equals your grid points would be ih, jh, where h is again 1 over n plus 1. and we're working on a domain 0 to 1 square, so just a rectangle or square of a side length 1. So what ends up happening is you end up getting -4 over h squared on the diagonal because of these terms appearing in both stencils. And here I can show you easily how to construct a matrix that if A1 is your 1D local Laplacian, then A2, your 2D Laplacian matrix, is equal to A1 Kronecker product with identity plus identity Kronecker product with A1. And in MATLAB, that's the function cron that does this. That just takes 2 arguments. Because Kronecker product takes one matrix and tiles it, multiplying each tile by the corresponding entries of the other matrix. And so one of these terms gives you partial derivative, second partial with respect to x. The other gives you second partial with respect to y. Unfortunately, this quick approach to getting the matrix in 2D cannot be used so easily up here because of the variable coefficient. So that's one unfortunate thing about that. But there are other ways that we'll see to make these kind of matrices, even in that case. Make sure I'm not overlooking anything. Okay. And like the 1D case, this stencil for 2D Laplacian is, dang it, is second order accurate. Okay. So questions about what's going on in 2D. And we'll come back to it later, talk about it more. But just, actually, does anyone have the homework assignment on them, like the handout? Okay. Oh, good. Okay. Yeah, the homework fortunately has just 1D problems. So, so that relieves me of responsibility to get much into 2D yet. I will have to later because in the notes I'm working on now, it's coming up more. Okay. Actually, this is a logical break time, and then I'll come back and talk about errors, stability, that sort of thing, things that come up on the homework. All right, so errors, or overall error analysis, covered this section. So to be concrete, I'm going to focus on basically Poisson's equation, u double prime equals f, which, as you see in other cases, leads to a system of equations. AU is equal to F. And I'm going to use U hat as a vector to contain values of the exact solution at all the grid points. Same old uniform grid that we've been using. So with that definition, with that notation, I can define the very important concept for error analysis, local truncation error, which you see in other classes for initial value problems. but now we're using for PDE. Similar idea though, is okay, it's a vector tau, which is AU hat minus F. So the idea is the vector, plain old vector U, those are the values of your approximate solution, which will solve this system exactly, except for any round-off error. So U hat, the exact solution, is going to satisfy this system approximately. There's going to be something left over, and that's a local truncation error. So if I were to define in words, no matter what kind of differential equation you're solving, ordinary or partial, initial boundary value problem, what local truncation error means is you plug in the exact solution into your numerical method. And since the numerical method is only an approximation, it's not going to satisfy exactly. What remains is your local truncation error. Now, the way we can try to assess the size of a local truncation error is using Taylor expansion. So that's what I'll do in this case with this example of Poisson's equation. So in the case of Poisson's equation, our A is 1 over h squared times this tridiagonal matrix. For the center difference second derivative stencil. So if I look at each element of this tau vector, tau sub I is equal to AU hat I minus Fi. So if I now fill in what AU hat is, so that would be 1 over h squared, and then I have UXI plus 1 minus 2UXI plus UXI minus 1, and then minus f of xi. Now, from the analysis of the stencil from yesterday, this approximation of second derivative is equal to the exact second derivative minus the error term. So minus the error gives us plus 1/12 h squared, and then fourth derivative of u at some at xi, and then it'll be whatever term is next in Taylor expansion for this stencil would be something that's order h to the fourth minus f of xi. But the PDE we're solving here, okay, technically it's an ODE, but anyway, is u double prime equals f. This is the exact solution. So those terms cancel out. So this right here is your local truncation error, or LTE. So we see that is order h squared. So using this system of linear equations to solve the PDE gives a solution that is second order accurate.
You mean it's h to the fourth?
Well, because this is a leading term.
What if you want it to be higher order than that?
Well, you have some choices, which are actually explored on the first homework.
Yeah, that's why I was asking.
Because what you can do is, if u double prime equals f, then fourth derivative of u is f double prime. So if you were to correct your system of equations, solving AU equals F, if you add a term that would match this error term, like on your right-hand side.
Oh, then it would cancel out, and you would be left with order
Order
8 to the 4th.
Yeah, so that's one way to do it, where you're still using the second order second derivative stencil, or you can use a higher order stencil for second derivative. That would involve 5 points instead of 3, and be fourth order accurate. So I think actually you have a homework touches on both of those approaches. But the first one is deals with something else we'll explore later called modified equation analysis. You basically modify the PDE to get something more favorable numerically, because your numerical method is meant to approximate to PDE, but there's some error involved in doing that. So sometimes by adding on an extra term to your PDE and approximating that in the same way, like using finite difference stencils and so forth, what you get in your system of equations might actually more faithfully reflect the PDE itself. There's a lot of tricks like that to improve the order of accuracy. And that's why this kind of error analysis is so helpful. To not just see, oh, the error is order h squared, but if we have some specifics about what the error looks like, that can give us a way to cancel it. Actually, my friend at Stanford, Margot Garrison, her student, by domain in geosciences, Danielle Maddox, is doing exactly that sort of thing, finding a leading error term and modifying the numerical method to cancel that leading error term. Okay. Now, local truncation error is one notion of error, but it's not what interests us the most. What we actually care about is global truncation error. GTE. Because I'll define that as the computed solution U minus the exact solution U hat. Because that's what we really want. We want the difference between the numerical solution and the exact solution to be small. The trouble is, this error can be a lot harder to get than the local truncation error. So that's why a lot of error analysis centers around that. But let's suppose I multiply both sides of this by A. So AE is AU minus AU hat. Now AU is equal to F, because our numerical solution is a solution of a system of equations. And then F minus AU hat, well, that's minus the local truncation error. So that's how the local and global truncation errors are related. So A times global truncation error is equal to minus local truncation error, at least for this kind of equation, where we boil it down to solving a system of equations. It's a bit more complicated than that for time-dependent problems. Although if you define things like residuals correctly, like you're doing in your research, Haley, it actually is the same idea. Okay. So what that means is your global error is a solution of a similar PDE than the one you're solving in the first place. So if I take this relationship, what this means is the error is an approximation to some function e of xi that again represents error. So ei is e of xi that solves this equation. Okay. Dang it. Alright. So someone fix one of those. E double prime of x is equal to minus tau of x. In the notes I have a minus on the other side too, that's not supposed to be there. On the interval 0, 1. And then same boundary conditions. So right now we're doing is, and I should have written that down earlier, that the original PDE, I'll just go ahead and write that here so you can add your notes. On 0, 1, and then homogeneous Dirichlet boundary conditions. Same boundary conditions apply in this case. So, but the thing is, now we have an idea of what tau is from our Taylor expansion. So we have E double prime of x is equal to, and I'll just use the leading term. So 1/12 h squared, fourth derivative. So I'm neglecting any higher order terms in h. See, I need to move this over. Okay. But the thing is, now I can just go ahead and integrate this. I can basically solve for my error. So E of x turns out to be minus 1/12 h squared u double prime of x. But then I have to add on constants of integration. So plus c1x plus c2, and these constants have to be chosen in such a way that, actually I'm going to factor that part out. These constants have to be chosen in such a way that the boundary conditions are satisfied. So all I have to do is, for instance, when x is equal to 0, I need to make sure I get 0. So I'll have minus u double prime of 0. And then if I choose x equal to 1, I have to make sure that everything cancels out. So this is going to be u double prime of 0 minus u double prime of 1 times x. So now I have at least a decent idea as to what my error is. The point I want to make is, and yeah, because of a mistake I made up here, there's a sign mistake in the notes here, but the minus is the correct sign. And notice it's also order h squared. That's the main conclusion I want to make here. So generally, the global truncation error is the same order of magnitude in terms of h as the local truncation error. Okay. So any questions about this kind of error analysis? So in fact, this is how, this is what Haley's doing for research, residual correction. If you are able to, where you're solving similar kind of DE with the local truncation error as your problem data, you solve that to get an error estimate, and then you can use that error estimate to update your solution and make it more accurate. So there are a lot of methods that use this approach. Okay, so now there are 3 essential concepts in error analysis for ODEs and PDEs that we need. There's consistency, stability, and convergence. So I'm going to define all 3 of these and explain how they relate to one another. Now, for a general BVP, boundary value problem, that ends up, so we're using spacing H, like in the uniform grid. You get a system of equations. I'm going to use the superscript H to refer to the grid spacing that is used. So we have this relationship in general between the local and global truncation errors. But what that means is the error is equal to minus AH inverse times tau H. So now what we can do is take norms of both sides. So the norm of the error, the global truncation error that we care about the most, is less than or equal to the norm H inverse times the norm of your local truncation error. But the thing is, what that means is, what if the norm of this inverse matrix is particularly large? The local truncation error can be amplified considerably to give you your global error. So the local truncation error might be small, your global truncation error, even if it's the same order in H, could still be large. So also, what happens as H goes to 0? This matrix might get more and more ill-conditioned, and so this norm can get larger and larger. We don't like that either. So that leads to this definition. So finite difference method that is used to come up with this matrix A. Well, I can really phrase it this way. The finite difference method described by A, because A incorporates, or AH, incorporates whatever stencil you're using, is stable if there exists some constant C and some particular spacing, grid spacing H naught, such that this norm that we're concerned about, that should be, I just are marking these typos here. They are supposed to be AH inverse, like I've written it here, but one place in the notes I wrote A inverse H. All right. So we want this norm to be bounded or less than or equal to, doesn't really matter. So we want this norm to be bounded independently of H, at least for H sufficiently small. H going towards 0 is what we care about. So that way, that helps ensure that the global truncation error cannot get out of hand in terms of size. Okay. So what we're saying here is uniformly bounded. Independently of H. And then again, at least for H is sufficiently small. It doesn't have to be for all H of any kind. Okay. So what that tells us is if it's stable, that gives us a bound on the global truncation error in terms of a local truncation error. So now that stability gives us a relationship between the two. Now, what kind of behavior do we really want for these two types of truncation error to make sure that our numerical method is an effective one?
Do you want the error to go to 0?
Yes, as a matter of fact. I was going to state that formally
Okay.
now, but yes. good you're in soon. Okay, so the definitions I need is, so a finite difference method of this form that's described by a matrix AH, it depends on the grid spacing, is consistent if the norm of the local truncation error goes to 0, as h goes to 0. And this is something that is generally easier to verify for local truncation error compared to the global truncation error. And so, for instance, in the case of a Poisson's equation example, we saw the error was order h squared. So yes, that is consistent. It does go to 0 as h goes to 0. But what we really care about is convergence. Convergent if the same behavior applies to the global truncation error, that it goes to 0 as h goes to 0. Now, those of you that are more linear algebra-y, I've deliberately not bothered mentioning what norm I'm using. But how come I don't really have to?
Because it's a norm equivalent.
Yes, that's exactly what I'm looking for. Yeah, norms are equivalent. That generally norms that we deal with are equivalent. And that if something is going to 0 in one norm, or even above one norm, but in a particular norm, then it's also going to go to 0 in other norms. All right, so I don't have to specify a norm. I can be lazy. Okay. So now that we have these notions of consistency, stability, convergence, here's how they link together. You lax Lax equivalence theorem, named after Peter Lax, who I'm betting he's retired by now. Was a professor at NYU. His name's going to come up a lot because a lot of things, when it comes to PDEs, are named after him. And I've actually met him from when he would visit Stanford. And, okay. Oh, well, he's still alive. He's 91 years old. So he's almost as old as my dad. A couple funny things about Lax, since we're doing pretty well on time here. When he would attend seminars, that's normally when I would see him, he would sit up in the front row and he would just fall asleep. He's like head all the way back snoring. But he already knew everything the speaker was talking about anyway, so I guess there was no need. But again, my own advisor, Gene Gollum, he would do the same. But I guess. Well, I don't think. Yeah, I think it's sort of habit because it's toward the end of the day and tired anyway.
Ironic considering his last name.
Yeah, I know. Yeah. And the other that I found interesting is that when he was giving a talk, because back then most speakers would, if this is late 90s or so, would use overhead projectors, and what most speakers would do is they would either have a pointer to point directly onto the screen, or they might just point their finger on the actual transparency, but not him. He would hold his finger out in the middle like this. It's like, wow, how do you do that? It just seemed kind of different. So, but we'll learn about certain finite difference methods that are named after him. So this is one of the most essential theorems that guides error analysis. And the nice thing about it is it has a fairly simple statement. So a finite difference method, AH is equal to FH, is convergent if and only if it is consistent and stable. And I'll show you the simple direction of the proof, that if it is consistent and stable, then it is convergent. So that would be this direction, based on how I've written it there. So what we have is, because of the stability, the global truncation error is bounded by this constant c that we know exists, at least for h sufficiently small, in terms of the local truncation error. But because of the consistency, so stability gives us this. But this is going to 0 by consistency. And norms cannot be negative. So because this is going to 0, therefore this is going to 0 as a result of both conditions put together. Yeah, so I have this relationship here. So in fact, you could say squeeze theorem. Okay. So we like to apply this theorem to the example I've been working with in the Poisson's equation. I've already shown you that it's consistent because the local truncation error is of order h squared. Now, granted, we've seen an expression for the global truncation error in this case, but I want to show why it's stable. So you can then apply Black's theorem to conclude that it is convergent. Also, besides the equation I solved to get the error in Poisson's case, solving an e double prime equals x, I only had the leading error term on the right side. It wasn't the actual local truncation error in full. So this would be a more rigorous way to show that, that it converges. So, so for a general symmetric matrix A, we have this relationship that the norm of A inverse, and this time I'll work with a specific norm, the 2 norm, which is the spectral radius, so absolute value of the largest eigenvalue of a matrix. So that's going to be the maximum of a reciprocal of any of the eigenvalues of A. Actually, I'll write it in here. So eigenvalue of A reciprocal. But that's just going to be 1 over the minimum of the absolute value of all of the eigenvalues of A. So in other words, if we get a handle on the smallest eigenvalue and magnitude of A, and show that that is bounded below independently of H, then this will be bounded above independently of H, which is what we need for stability. So we need to have some understanding of the eigenvalues. Now, for general finite difference schemes, that's actually very difficult to get a hold of those eigenvalues. Maybe best you can hope for some estimates. But in this case, we can. We actually have a formula. So for so for u double prime equals f, this is what we have in this case. The formula for the eigenvalues, it's 2 over h squared cosine p pi h minus 1. Now for u double prime, the matrix is negative definite. So we know that cosine is less than or equal to 1, so all these eigenvalues are going to be negative. And this is for p equals 1 to up to n. So in fact, like when p is equal to 1, h is small, this is close to 1. So we're going to get an eigenvalue that is negative but close to 0. Now what I can do, though, is do a Taylor expansion of cosine. So cosine is equal to 1 minus p pi h squared over 2 plus more terms that are order h to the 4th, and then minus 1. And the 1s will cancel. So now what's going to happen is, notice the in the leading term, the h squareds are going to cancel out. The 2's are going to cancel out. So this is going to be equal to minus p squared pi squared plus, and then this is order h to the 4th, but it's divided by h squared, so order h squared. Okay. So, so in fact, so as h is going to 0, the smallest eigenvalue magnitude is going to be minus pi squared. So all of the eigenvalues are effectively going to be bounded by pi squared plus something order h squared. And h is going to 0. So, so what we can conclude, I mean, to be really rigorous about it, we should see, like, what is the this next term here. But but we would know that based on the Taylor expansion of cosine. Okay. But because this is going to 0 anyway, what we can conclude is that the eigenvalues are at least bounded away from 0. Therefore, this minimum here is roughly 1 over pi squared. So, and because this is independent of h, that's the key here. We can get a bound that's independent of h. That way we can conclude that the norm of A inverse is uniformly bounded independent of h. So we can conclude from here that we have stability, and we already know the local truncation error is going to 0, so it's consistent. Therefore, by Lax equivalence theorem, we know it's convergent.
What happened between the second to the last row and the last row? I'm sorry, from there to there.
Here to here?
Yeah, what did you?
Oh, all I do is I replace cosine p pi h with its Taylor expansion. Okay. Okay. So at least for this relatively simple case, because we get the eigenvalues, we could prove convergence. So what comes up on the homework is using certain Taylor expansions to get a handle on how the error is behaving, like to show something second order accurate, or you see what the leading error term is, so that you can try to deal with it to get fourth order accuracy, things like that. So what you would do for a general PDE, if you're trying to get local truncation error, here's what you would do. You would assume that u of x is your exact solution. You would, and so then for whatever derivatives, you would have a stencil. So then you would plug all your u values into that stencil and do Taylor expansions to get as simple expression as you can, where the idea is, like, let's suppose your PDE is like u x x x x is equal to f, for example. Then what you would do is you would have a finite difference stencil for fourth derivative. So you would have like u of xi plus 1, u of xi minus 1, etc. And you would plug in those Taylor expansions around xi into your stencil, simplify whatever you can, and what's going to pop out is the exact fourth derivative which will cancel with f, because it's the exact solution, and then it's the terms that are left over that will give you the local truncation error. And you want the one that's of lowest degree in h, because that's the leading term. So Taylor expansion is the key. And using effect, you're plugging the exact solution that is known to satisfy your original differential equation. So those two things together cause the local truncation error to pop out. So let's see. Well, I've come to the end of the notes. So I'm glad I made it all the way through. Finite difference. So, and as I mentioned before, I want to hold off on covering spectral methods until I feel that it seems like everybody's in good shape with the homework. During what time, few minutes we have, 10 minutes today, we can talk about it.
The homework?
Yes.
I don't think I have any more questions.
Well, okay.
It's generally that I just don't have things.
Okay. Okay, well, yeah. Well, it wasn't until today that I covered what you actually needed. Yeah, so it's kind of difficult to have any understanding before today, or before this hour. Okay. Yeah, but what I'm prepared to do, since in the overall scheme of things, we're in good shape as far as getting through the stuff. We can take time on Monday also. To go through it, and well, then maybe everybody will be here too. So, well, I'm happy to stop if nobody has questions. But okay, well, it is Friday.
I like the latter half of this week better than the first half of this week. The first half of this week, I was like, I don't know. This is better.
Yeah, well, that was actually numerical. But yeah. Yeah, the first part was kind of like a 606 redo. And even I didn't like teaching that class.